Hello and welcome back to Sudoku Swami's pencil and paper method. Today we'll be going over some basic terms that you should familiarize yourself with so that you will always know what I'm talking about whenever I refer to a specific thing or a particular concept in the upcoming lessons. So without further ado, let's get right to it. Sudoku is played on a 9x9 grid that looks like this. This is called the grid. And the grid is divided up into several subsections. It has 9 horizontal rows and 9 vertical columns and 9 3x3 subgrids that are called blocks. And the rows are numbered 1 through 9 from top to bottom. The columns are numbered 1 through 9 from left to right. And the blocks are numbered 1 through 9 as you see here, 1, 2, 3 across the top, 4, 5, 6 in the middle, and 7, 8, 9 on the bottom. The smallest divisions in the grid are called cells. These little squares are where we enter the numbers into the puzzle. And again, they are called cells. As you can see, there are 9 cells in every row, column, and block. When the puzzle is solved, each row, column, and block will contain the digits 1 through 9 with no repeats and no number left out. And further, each row, column, and block is also called a house because they house all the digits 1 through 9. Here you can see that row 2 contains all the digits 1 through 9 with no repeats and no number left out. And likewise, column 5, no repeats and no number left out. And again, in block 3, all the numbers 1 through 9 with no repeats and no number left out. There is one more subdivision called a chute, like a laundry chute. A chute is 3 blocks in a row, either horizontal or vertical. This is a chute, and these are the 3 horizontal chutes, and these are the 3 vertical chutes. And notice that this is not a chute. A chute cannot be diagonal. It must be either horizontal or vertical. When I am referring to a particular number in the puzzle, I will use the word digit, like digit 1 or digit 7. And this can mean a particular digit 7 or all of the digit 7s, and you will know which based on the context. When we want to refer to a specific cell in the puzzle, we will use the row number and the column number. Like this cell would be row 3, column 2. Or R3C2. The designation R3C2 is known as the coordinates of that cell. Likewise, this cell would be row 8, column 9, or R8C9. And this cell would be row 6, column 4, or R6C4, and this cell would be row 1, column 7, or R1C7. When you are presented with a new puzzle, there will already be some numbers filled in to give you something to start with. These numbers are called givens. And generally speaking, the more givens, the easier the puzzle will be, but that is not always 100% true. In order to be considered valid, a Sudoku puzzle must have only one unique solution. And it has been proven that the minimum number of givens necessary to create a puzzle with one unique solution is 17. When we place a digit into a cell as the solution to that cell, we will call that the cell's value. Like this cell's value is 3. Now when you enter that 3 as the solution to that cell, it will appear in 3 houses at the same time. It will occur in a row, and it will occur in a column, and it will occur in a block. And it will be the only 3 in that row, column, and block. When you are solving a puzzle using a computer or smartphone app, you will see a lot of little numbers in all the unfilled cells like this. These little numbers are called candidates, like candidate 3 or candidate 7. Some people call them pencil marks or notes, but we will call them candidates, meaning possibilities. The candidates represent the remaining possible values for each cell. But because we are learning to do the puzzles with pencil and paper, we will be filling in the candidates by hand. And we will always try to do this in a very economic fashion in order to keep everything as legible as possible. We're not going to enter all the possible candidates. That would take way too much time and would end up being very messy. We will only enter candidates here and there under some very specific conditions and circumstances that I will describe in detail in the next lesson. For convenience sake, I will be entering the candidates with my computer mouse like this. But you will, of course, need to do this by hand. In any event, I would recommend using a number 2 pencil to enter the candidates because eventually they will all be erased as we replace them with actual solutions to the cells. You will need to erase them from the cell where you enter a value, and you will also need to erase them from other cells where they are no longer possibilities. This is why we will only enter a few of the possible candidates, i.e., only those that are necessary to help us solve the puzzle. We want to keep the grid as clean looking as possible. And I would also highly recommend using a large handheld soft rubber and good quality eraser. The little erasers on the opposite ends of most pencils are terrible. They get dried out quickly and end up shredding and damaging the paper on your puzzle. And I would only use an ink pen after you are absolutely sure you have deduced the correct value for a cell. This way, you can easily read what you have accomplished without destroying the surface of the page. Now let's talk about subsets. A subset in Sudoku is defined as n number of candidates in n number of cells, with n being any number between 2 and 9. In other words, 2 candidates in 2 cells, or 3 candidates in 3 cells, or 4 candidates in 4 cells, and so on and so forth. There is a slight semantic problem with this definition, so let me try to clarify it. When we say 2 candidates in 2 cells, we mean the same 2 candidates. And when we say 3 candidates in 3 cells, we mean the same 3 candidates. Capiche? And remember, all the candidates and all the cells of any subset must be contained entirely within at least one house. Pairs and triplets can sometimes lie in 2 houses at the same time, but we will address that in the next video. Subsets of 2 candidates are called pairs. Like here in block 1, we have a pair of 2 and 3. And in row 6, we have a pair of 7 and 6. And in column 8, we have a pair of 5 and 8. And subsets of 3 candidates are called triplets or triples. Like here in row 2, we have a triplet of 1, 5, and 9. And down here in block 9, we have a triplet of 4, 5, and 7. And over here in column 1, we have a triplet of 8, 2, and 3. Okay? And as you have probably already guessed, subsets of 4 candidates are called quads or quadruplets. Here in row 1, we have a quadruplet of 1, 2, 5, and 9. And in column 1, we have a quadruplet of 3, 4, 7, and 8. And down here in block 9, we have a quadruplet of 1, 3, 6, and 9. In this pencil and paper course, it will be a rare occurrence when we will need to consider any subset greater than a quad, okay? So there's no need to freak out, at least not yet, ha ha. And please note that in subsets of 3 and higher, it is not necessary for all the candidates to be in all the cells. Like here we have a triplet of 1, 5, and 9 in row 2. But if there were a 5 filled in this cell, and there were a 9 filled in this cell, that would eliminate the 5 from this cell, and it would eliminate the 9 from this cell. But that would still be a triplet in row 2, because those 3 cells would have to be solved for those 3 candidates. So as long as you have at least 2 of the subset candidates in each of the cells, it's going to function as a subset. When we are solving puzzles with only pencil and paper and without automated and complete candidate lists, here is a common example of what we might see and what we will know from it. If we have a house with 7 solved cells and 2 unsolved cells like this, we will know that there is a pair in those last 2 cells. Like here in row 2, we have all the digits except for 2. So we have 1, 2, 4, 5, 6, 8, and 9. So what's missing? The 3 and the 7. So these two cells must be solved for 3 and 7, and that's a pair. That's a subset of 2. So even though we don't know which is which yet, we know that one of those two cells must be a 3 and the other one must be a 7. Two candidates in two cells. And likewise, if we have a house with 6 solved cells and 3 unsolved cells, then we will know that there is a triplet remaining in these last 3 cells. Like here in block 4, we have all the numbers placed except for these 3 cells. So we have 1, 2, 4, 5, 6, and 8. So these 3 cells must be solved for 3, 7, and 9, even though we don't know which is which at this point. But those 3 cells are a triplet, 3 candidates in 3 cells. In the next lesson, we will talk about what we will do whenever we encounter these types of situations and which candidates we will enter, if any. Whenever you have a cell where there are only 2 possible remaining candidates for that cell, this is called a bi-value cell. Bi meaning 2, like a bicycle has 2 wheels. In a bi-value cell, one of the candidates must be true and the other must be false. When you are solving puzzles with a computer program or a smartphone app and you see just 2 candidates in a cell, you can be sure that it is a bi-value cell. Like here in this puzzle, all these highlighted cells are bi-value cells. Each one of those cells contains 2 candidates, and in each one of those cells, one of those 2 candidates must be true and the other must be false. But please be aware that when we are solving puzzles with pencil and paper and we are entering candidates by hand, we might sometimes see 2 candidates in a cell that we entered one at a time, but it will not always mean that it is a bi-value cell like this. Here in row 2, we might enter 2 candidate 8s in these cells because they could both contain an 8. Notice that there is an 8 up here in row 1, and there is an 8 in row 3, and there is also an 8 in column 1. So these are the only 2 cells in block 1 which can contain an 8. And then if we look at the 4s, we can see there is a 4 in column 1, a 4 in column 3, and there's a 4 in row 3. So that means these 2 cells are the only 2 cells in block 1 that can contain a 4, and we might fill them in just like that. But this cell, even though it contains a 4 and an 8, this is not a bi-value cell. It looks like a bi-value cell, but this cell could also be a 9. If you notice, there is no 9 in row 2, and there is no 9 in column 2, and there is no 9 in block 1. So that could be a 9. So really there are 3 candidates for this cell, but as we are filling in the candidates in an economic way, like I said we're going to do, we may see it look like this. And whenever this happens, we need to continually be aware of when these are bi-value cells and when they are not bi-value cells. We have to pay very close attention to this important difference. More about that in the next lesson. When there are exactly 2 possible remaining instances of a particular candidate within at least one house, we will again know that one of them must be true and the other must be false. And when this is the case, we call these 2 candidates a conjugate pair. Like here in this diagram, we see there is a 6 in row 1 and there is a 6 in row 2, and the 1 is blocking this cell in row 3, so we know one of these 2 cells must contain a 6. And down here there's a 5 in row 8 and there is a 5 in row 9, and this 2 is blocking this cell in row 7. So these 2 cells are the only 2 cells in that block, and in that row for that matter, that can contain a 5, and we can enter those 2 candidate 5s in those 2 cells. So we know one of these 6s up here in row 3 must be true, and we know one of these 2 5s in row 7 must be true. Therefore, they are conjugate pairs. Those 2 6s are a conjugate pair, and these 2 5s are a conjugate pair. But please note that the 2 candidates in a bi-value cell also have this same relationship, i.e. that one must be true and one must be false. But the 2 candidates in a bi-value cell are not called a conjugate pair. This is because they will always be different digits. The term conjugate pair applies only to same-digit candidates, like you see here. Got it? All right, now let's talk about what we mean by the term seeing each other. First, let's talk about cells. In order for two cells to see each other, they must be in the same house. This is the only way. Like these two cells see each other because they are in the same row. And these two cells see each other because they are in the same row. And these two cells see each other because they are in the same column. And these two cells see each other because they are in the same column, column 9. And these two cells see each other because they are in the same block. And these two cells see each other because they are also in the same block. But be careful. Notice that these two cells, even though they are touching at the corners, do not see each other. This cell down here is in row 4, column 6, and block 5. And this cell up here is in row 3, column 7, and block 3. They do not share any house in common. But here is something interesting. Notice that these two cells do not see each other. But this cell can see both of them. It sees this cell up here because it's in the same row, and it sees this cell down here because it's in the same column. And here's another example of the same thing. This cell and this cell do not see each other, but this cell can see both of them. It sees this blue cell up here because it's in the same column, and it sees this blue cell over here because it's in the same block, this house, block 5. Now, even though those two cells look like they're out of line, they do see each other because they lie within the same house. Please note that any two cells that can see each other cannot have the same value. Two cells that can see each other cannot have the same value. That's a law. Because if they see each other, they must be in the same house, and we know that any particular digit can only occur one time in any given house, according to the basic rules of Sudoku. And now let's talk about candidates seeing each other. We don't need to spend much time on this because when we are solving puzzles with only pencil and paper and without complete candidate lists, this is not going to come up very often, but you should still understand these concepts and how this works. Here it is in a nutshell. In order for two same-digit candidates to see each other, they must both lie in the same house. And in order for two different digit candidates to see each other, they must both lie in the same cell. Here are some quick examples. These two candidate 7s can see each other because they lie in the same column. And these two candidate 7s can see each other because they lie in the same column. And these two candidate 7s can see each other because they lie in the same block. But these two 7s do not see each other because they do not lie in the same house. And likewise, this candidate 2 can see this candidate 2 because they lie in the same house, row 4. And this candidate 2 can see this candidate 2 because they also lie in row 4. And this candidate 2 can see this candidate 2 because they lie in the same block, the same house. But this candidate 2 does not see this candidate 2 because they do not lie in the same house. To repeat, in order for two same-digit candidates to see each other, they must both lie in the same house. It's as simple as that. Now let's take a look at different digit candidates. In order for two different digit candidates to see each other, they must both lie in the same cell. Like this 7 can see this 2 because they lie in the same cell. But this 7 cannot see this 2. Okay? And this 7 can see this 5 because they lie in the same cell, but it cannot see this 5 over here. And this 7 can see this 9 because they are in the same cell, but it cannot see this 9. It doesn't matter that they lie in the same house. In order for two different digit candidates to see each other, They must both lie in the same cell. Like this 9 can see this 1 because they are in the same cell, but it cannot see this 1. Okay, enough about that. Let's move on. All right, the last thing we're going to talk about today is the intersection of two houses. For instance, up here we have the intersection of row 1 with block 2. The 3 yellow cells are the intersection cells. Those 3 yellow cells lie in row 1 and they lie in block 2. And down below you see the intersection of row 8 with block 9. The 3 yellow cells are the intersection cells. They lie in row 8 and they lie in block 9. And here we have the intersection of a column in a block. On the left we have the intersection of column 2 and block 4, and on the right we have the intersection of column 9 and block 3. Now when a row and a column intersect, they only intersect in one cell. That yellow cell is the intersection of row 3 and column 8, and here the yellow cell is the intersection of row 5 with column 2. Okay, that's it for now. There will be many more terms for you to learn as we move through the course, but if you're with me on what we've discussed today, we're good to go. So I'll see you in the next lesson where we will talk about our basic approach to entering candidates by hand into the puzzles. In the meantime, be well and be happy.